All right, this is the Chapter 6 lecture, so let's get going. All right, Chapter 6 is about game theory. The whole purpose of the game theory chapter here is to model decisions of individuals, and we need game theory because it takes into account that the decisions or the rewards for making a decision depends on the decisions made by others, okay? If your reward doesn't depend on decision making of others, then game theory is not going to apply. Example might be the rock, paper, scissors. So whether or not you win the game depends on whether or what the other person chooses. So in social network settings, game theory can help predict what kind of decisions people make based on their position in a social network. That is, with talking to other people, interacting with other people, that affects their decision-making process. It can also help predict the consequences of those decisions. So the decisions might propagate through the network and they might affect the formation or destruction of edges in the network. A nice example for this is people thinking about getting vaccinated. There's been a big thing about anti-vaccination, and you have to understand, or you hopefully understand, that when people make decisions about whether or not to get vaccinated, it's affected by whether other people get vaccinated. So if everyone else gets vaccinated and I don't, then I am not going to have get into any trouble. If a whole bunch of other people also don't get vaccinated, then we all might be in a big whole world of hurt. So again, this is about decision making, where your decision making or your consequence is influenced by what other people do. So there's a couple of big assumptions to game theory. The number one assumption here is that the decision maker, I guess this is really two assumptions. Number one is that the decision maker knows all the possible decisions, okay? So the decision maker knows all the possible courses of action, okay? This is a pretty good assumption, or not a good one. This is a pretty hard assumption to make about, generally speaking, because there's times when you don't know all the decisions that are possible. The second one is a pretty big one too, and that is the decision accounts for all of the corresponding rewards. We're going to talk about a bunch of these decisions, and there might be a time when like, hey, I just want to help this other person out a little bit. Well, for an economist, all of that is formulated in the reward function. So when we see the rewards, we're going to make sure we have it. Okay, or we have all the rewards in there. So number one rule is sort of all the information is contained in our definition of the game or description of the game. The other big assumption is that the decision makers make their decisions independently, meaning they aren't correlating their decisions sort of with other people or based on prior decisions. And the second one is, and this is a huge one, they're making their decision rationally. And over here we have a nice one. This is a vaccination decision. If you are choosing whether or not to vaccinate, you're going to lose the cost of the vaccination, the time you spent. That would be, you got to think of all the corresponding costs and rewards. So the time you spent, the actual amount of money you spent, everything would be contained in there. For the people who didn't get vaccinated, their cost would be this risk of infection, and there would have to be a number implied on it. And then here we have this sort of, the individual cost of the other person. So I guess the point here as we go to the next issue, there's plenty of times that the assumptions are broken, okay? So cognitive biases are going to affect the amount of decisions you search for. So you may not even consider all the possible decisions. I'm not going to get into what those cognitive biases are. The cognitive biases also can influence the reward calculations, and in addition, where you are in your social network, or what's going on around you, like where your edges are, that also affects your information availability. All right, we're going to keep going with this. Okay, we've made some pretty significant assumptions that kind of narrow what's going on, but we're going to keep going with it because in our world, if you have enough independent decisions by one person or two people sort of making decisions together, or a huge number of decision makers, we can assume that rationality is sort of there at the mean. That is, within a certain range, it's going to be rational. So if you think about like this person here, like, oh, I just saw this news, the Dow is down, I'm going to sell all my stocks and get out of it. Well, at the same time, there's probably other decision makers that are like, oh, I think other people are going to be selling, so now is a great time to buy. And so they sort of cancel each other out, and we can go with it. So we like game theory, and we'll see later as the rest of this course evolves, the game theory really helps sort of model the decision making, and it gives us a nice, in some cases, a nice mathematical basis for it. So it's really fun. All right, how do we do this? The first step in doing game theory is to diagram the game. So in a game, usually we'll have just two players, okay? Two players is the way we do it. People are trying to do three-dimensional, four-player games, blah, 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 blah. We aren't going to deal with that for now. We're just going to deal with two nodes or two players in our games. So we got two players, they're interacting with each other, they're each making a decision, the decision depends on the other person. We're going to diagram the strategies. So we have the set of options that each node can do, and then we're going to have a payoff. That is the reward received by each node given the two strategies that each player chose. So we'll do rock, paper, scissors first. That's a fun one. Rock beats scissors, scissors beats paper, paper beats rock. All right, so here's how the actual decision matrix would look, and this is the type of decision matrix we need to be able to make as a network economist. And here we go. So on the top, we've got, or on the left, the rows is player one. So we got player one listed, that's you. And you can either choose rock, paper, or scissors. The player two, that is your partner, they're listed in the columns. They can also choose rock, paper, or scissors. Now if we look at the boxes themselves, so within the matrix, each box shows the combination or the reward for that decision combination. The first number is player one's payoff. The second number is player two's payoff. So if you choose rock and your partner choose rock, that's even, no winner. If you choose paper, your partner chooses rock, you win and your partner loses. So in this case, we're saying you get 1 point, your partner gets -1 point. If you play scissors and your partner plays rock, then you lose, you're -1, and your partner gets 1, and then there we go. So that's lovely for rock, paper, and scissors, and you can see there that you can, what you're trying to do is play the optimal thing against what your partner does. So rock, paper, scissors, hopefully we're all familiar with. Now, we get to quantify it though. In a lot of cases, we'll have a strategy that works better or worse than another strategy. And so when we think about a player A and a player B, in this case, it's player A is choosing to go up or down, and player B is choosing to move left or right. I'm not sure what this means in the real world, but this is what we do a lot in this. But anyway, we got two different strategies for each player. And what we want to do is see, whether or not or which strategy makes the most sense. So we draw out player A, player B. We put in the possible decisions, and then we make the matrix that has all of the combinations of rewards in it. So, number one thing you got to think of, the response. If you have what's called a strict best response, what we're doing here is we're looking at what one player chooses, what is the other player's best response. Okay? And there's two levels of best response. There's best, which is just okay, and then there's strict best, which that's kind of the awesome one. Okay? So if we look at this matrix and we say player B is going to choose R. So if player B chooses R, player A's best response is U. Not only that, this is what's called a strict best response. A strict best response means I get more for it. Okay? If it was just that player A, in responding to R, got the same reward, it's still a best response. Like it's still equal, but a strict best response means it's greater than. So if we flip that down to best response, and we give it to, given the other player's choice, a best response only gives you an equal reward. So in this little matrix here, if we knew player A was going to choose D, player B could either choose L or R. Okay? So a best response for player B to D is to choose R, but also a best response to D is to choose L. So this is kind of a weird thing to think about, but we're going to show you sort of the implications later. All right, the next step in this process is to identify, is there really just one strategy that's going to be the one that works best for either player? The first kind of strategy is the one that's the clearly best response. And that is to say, if we can look at a matrix and say, in response to whatever the other player does, I might always have a strict best response, then that's always going to be my best thing to play. If you look at this matrix, if player B chooses L, player A's strict best response is to choose U. So they're going to get 8 instead of 7. If player B chooses R, again, player A's strict best response is to pick U. They're going to get 6 instead of 4. We call U then a strictly dominant strategy for player A, meaning it's always the best choice. Always, and you always get a better reward. A dominant strategy is sort of like the previous one where we had like a best response. So for a dominant strategy, what we're saying is it makes sense to play this. Yes, you get at least as good of a reward. This is the equal to or greater than. So if you look at player B, you can see that if player A is going to play U, then player B has a strict best response of playing R. They're going to get 8 instead of 6 for playing that. If player A plays D, then player B is somewhat indifferent, right? They could play L or R and get the same reward. So L or R is a best response. In this case, we would say, hey, why not play R? So that would be why you'd say R is a dominant strategy for player B. It's at least as good or better than any other response to any other strategy by player A. When we're talking about the equilibrium, so where is it that the players are going to pick? What are the two strategies we expect to see? And the easy one to note is if there's a player that has a strictly dominant strategy, the other player is going to choose their best response to that. Okay? So in this case, player A, their strictly dominant strategy was up. So player B is going to play their best response to that. And you remember we still had strict best and sort of regular best. So if it was just a best response, we may not be sure what player B was going to say. But in this case, R is a strict best response to U, and therefore the equilibrium is here going to be UR. Okay? So no player here has any reason to change strategies. All right, it gets a little more complicated if there's not a strictly dominant strategy. What we're doing here is we have players that are choosing the best response to the other players. I've set up a matrix here. This is out of the book for firm 1 and firm 2. We have a situation here where firm 1 is too small to get anyone's business alone. That is, if they go and solicit a firm that firm 2 didn't even talk to, they get 0. Firm 2, though, is too small to get firm A's business alone. So firm A is just the biggest firm or the biggest business around, and then firm 2 isn't even big enough for them. But if they both go together, they can get A. If they go together and get B, then they split the difference. If they go together and get C, they also split the difference. But note here, we've got an option here because firm 2 can go it alone and get another firm. So, in this matrix we have firm A having A being the strict best response to firm 2 choosing A. They have B as a strict best response to firm 2 choosing B. And they have C as a strict best response to firm 2 choosing C. That means they always get more money. Now, firm 2, on the other hand, yes, they get more money if A chooses A. So if they pick A, or if they know firm 1 is choosing A, they will definitely choose A. However, if they know firm 1 is choosing B, it makes the most sense for them to choose C because they're going to get 2 points or 2 reward. And at the same time, if firm 1 chooses C, then firm B has the best incentive, or they're going to choose, firm 2 is going to choose B. So what happens here is we're going to say, basically talking about equilibrium, if the player's choice is the best response to the other's choice, the player is going to continue making the same choice. On the other hand, if the other's choice is the best response to the player's choice, there's no reason for the other one to change. And what that means on a bottom line here is, especially for firm 2 that can switch and gain a profit, we would expect firm 1 to look at the matrix and say, look, I'm not going to choose B because I know if I choose B, then firm 2's best response is to choose C. I'm also not going to choose C because if I choose C, then firm 2's best response is to choose B. If I choose A, their best response is A, so that becomes the equilibrium. All right, so equilibrium and optimality are sort of two different things. And usually when you start talking about optimality, it's because an equilibrium isn't what you really want as a result. So in this little matrix over here, I'm showing the hunt stag, hunt hare option. This is a coordination game. And here, the best option, you'll see, well, if you look at the equilibriums, we have hunt stag being the strict best response to hunt stag, and hunt hare being the strict best response to hunting hare. And therefore, there's actually two equilibria here, meaning it's possible if we're both hunting stag that we're just going to stay hunting stag. That's the best response. If we're hunting hare, then we're going to stay hunting hare. That's the best response. The problem with that is we could do better. And this is where the idea of Pareto-optimal comes in. Pareto-optimal in this situation means if we're both hunting stag, that's the best option for both of us. If we're both hunting hare, it might be an equilibrium, but there's that better option that we didn't hit. So Pareto-optimal is an issue that really arises or becomes important when we have a situation where the equilibrium is something that overall isn't as good as it could be. Socially optimal is about the same notion. That is, given this certain equilibrium we're at, would it be better to move to a different place? And in this case too, the hunting hare is not socially optimal. If we coordinated our efforts, we could hunt stag and both be better off, or the total of it be better off. So the difference mainly between Pareto-optimal and socially optimal is that Pareto-optimal just means no one else can be better off by switching, where socially optimal means the sum of the two rewards could be better if they chose different options. All right, we're just going to do a few little exercises now and talk about the Nash equilibria and whether or not they're Pareto or socially optimal. So first problem up here. We're back to up, downs, and left and rights. In this payoff matrix, if we look at it, we can see that for player A, considering what player B does, if player B is going to choose L, player A's strict best response to L is going to be to play D. And if player B plays R, U is player A's strict best response. Looking at player B's options, we can see R is the strict best response if the player A chooses up, and L is a strict best response if player A chooses down. Therefore, we have two equilibria. That's the down and left with payoffs of 3 and 3, and up and right with payoffs of 4 and 2. Now remember, Pareto-optimal means can we get a better reward for either one without infringing or lowering the reward for another one. So the down and left at 3 and 3, we are Pareto-optimal. We can't move to another result that pays better for at least one person without hurting the other one. At the same time, over in the up and right, it's the same thing, okay? Yes, if we move to left and down, it would be more equal, but you are still Pareto-optimal if you can't lower anyone else's reward. So I can increase player B's reward by moving, but I can't do that without decreasing player A's reward. So again, it doesn't make sense to talk about these unless we're talking about we're sitting in an equilibrium to talk about socially or Pareto-optimal. You can see that up and left, that's not Pareto-optimal or socially optimal, and neither is down and right. But it doesn't make sense to really talk about it because those just wouldn't happen. The players wouldn't pick those strategies. And if they did, then you could explain it to them. All right, next problem. All right, we tweak the matrix a little bit. It's still up, down, left, and right. In this situation, up is a strict best response to right. Down is a strict best response to left. Looking at player B's options, R is a strict best response if player A chooses up, and R is a strict best response if player A chooses down. In this situation, R is strictly dominant for player B, so of course they're going to pick R. And in that case, A is going to pick U. So we're up here in this upper right corner. Pareto-optimal, yes. We can't move out of this cell, increasing someone's reward without decreasing someone else's. Sure, player B is ruling it. They're getting 20 out of this, and no, poor A is only getting 4. But we are Pareto-optimal because we can't move somewhere that's going to get a better reward for A without decreasing player B's reward. Socially optimal, interestingly, this one is socially optimal because the total payoff is 24, and there's not a better payoff anywhere in the matrix here either. All right, one more time. Up, down, left, and right. New matrix. If you look at this matrix, let's look first at player A's options. We can see here if player B chooses L, player A is best off choosing up. If player B chooses right, player A is also best off, strictly best off, picking up. In this little matrix, U is a strictly dominant strategy for player A. Now, if you look at player B, L is a strict best response to up, while R is a strict best response to down. And here's where the little twist comes, and you gotta remember this. U is strictly dominant for player A. A is going to play U, no matter what, okay? That means up and left is going to be the equilibrium. As much as player B would like player A to choose down, they are not going to do it, okay? So up and left is the equilibrium, whether or not player B wants to or not. Now, this one is Pareto-optimal. It is socially optimal. Y'all can do the math on that one yourselves. All right, last one. This one's got a little twist, huh? Up, down, left, middle, and right. So, what are we going to do here? Well, one of the things you can do actually pretty simply is, or first thing to try is eliminating one of the options. So let's see what our best responses are for player B to player A choosing up or down. Okay, so for player A, if they choose up, player B's best response is L. That's a strict best response. If player A chooses down, player B's best response, strict best response, is going to be to choose R. So you see for player B, the middle option actually doesn't even come into play. So you can actually just eliminate that from the thing. Given that, we can just go with what is the best response if player B chooses left or right. So we have, if player B chooses left, player A's strict best response is to choose up. If player B chooses right, player A's strict best response is to choose up also. So interestingly, if we did this, player A is going to always choose up, and player B's best response to up is left. So actually, up and left is the equilibrium of this one. So even though you can see like maybe that middle down would work and that right down would work, it doesn't really work in sort of the final end play. Because remember, no one gets to choose what the other player does, and so you can't sort of force someone. Like player A would love to force player B to choose middle, but it's not going to happen. We pick our strategy based on our own payoffs, not based on the other person's payoffs. All right, so that was our game theory chapter. That was very exciting, and I'll see you next time.